Okay, so in the last class we had derived this relationship, how the forces and moments are related to the kinematic quantities V and K. So if there is a strain energy function, we take its derivative with respect to strain measures and then we get back the forces. Similarly for the moments. Okay? And then what's the meaning of del psi by del V1, for example? If I write down del psi over del V in terms of its three components, it's del psi over del V1, then del psi over del V2, and del psi over del V3. So what do each of these three components mean? So if you want to understand that, let's suppose we have the force vector n acting here in some arbitrary direction, okay, the vector n, the contact force, internal force on a cross section, okay. So you could write that as n equal to, let's say, ni ei, right, in the basis of the global coordinate system E1, E2, E3. And we could also decompose this in the local basis of the directors. So if we do that, this is same as some other component ni di, right? And then, so we get the three components here. So n1 comes with d1, n1, then n2 comes with d2, and n3 comes with d3, right? And you can see they have got physical meanings. What's the meaning of n1, for example? So you see, it's the result, it's the component of this force along d1. Oh yes, right, this is capital N. Thank you. Capital N1, capital N3, okay. So capital N1, what is its physical meaning? Shear force, right? Shear force along d1 because it's parallel to the cross section. Similarly, capital N2 is the shear force along d2. So N1 and N2, they mean shear forces, whereas N3 is the axial force because it is parallel to the cross section normal. Let's see how these three quantities are related to the derivatives of psi with respect to V. So we will write again n equal to ni di, right, which is same as, now di you write as big R times ei. So this becomes big R ni ei, isn't it? And if you allow me, I could write this as big R times n1, n2, n3, right? So I just wrote it down in a column vector n1, n2, n3. And if I see from here, this is also equal to big R times del psi over del v, and then I further write del psi over del v in this form. Okay. Now, we relate these two, and what do we see? So, this big R they cancel, and we simply get that n1 is del psi over del v1, even better, right, and n2 is equal to del psi over del v2, and similarly n3 is equal to del psi over del v3. So, you see, if you want to get shear force along d1, you simply take the derivative of psi with respect to shear strain along d1 v1. Same thing goes for n2 and for n3. Similarly, you could also decompose your moment here. So, if there is a moment m acting here, you could decompose that along the three directors d1, d2, d3. So, m, either you write as small mi ei in the global coordinate system or in the local coordinate system with big mi di. And then what is the meaning of big M1, big M2, big M3? Big M1, for example, is the component of this M along D1. So, you see you have moment along D1. So, what does that mean? Yes?
Torsion?
Torsion?
Oh, M3 is the torsion.
M3 is the torsion, isn't it? The moment along D3.
And M1 and M2 is for bending.
Yes, it is for bending moments. So, the moment along D3, big M3 for example, which is along the cross section normal, it will try to locally twist your cross sections. So, it is going to locally twist the beam, therefore, it is twisting moment, whereas M1 and M2 are going to locally bend the beam, therefore, it is bending moment, right. So, in the similar way you could also derive that M1, M2 are bending moments, and M3 is the twisting moment. Furthermore, M1 is equal to del psi over del K1. So, if you want to get bending moment along D1, you simply do del psi over del K1, where K1 is the bending curvature along D1. Similarly, big M2 is equal to del psi over del K2, and big M3 is del psi over del K3. Okay. All right. Okay, having done this, still I don't know what is this psi. Right, the question is what's the form of this psi? Psi as a function of v comma k. What is this? How does its mathematical form look like? You know, is as in 3D elasticity, you have W, the three-dimensional strain energy density. When you say it's a function of deformation gradient, and then you also establish that P, the first pk, is del W over del F. Okay, so that's very good. You got how the stress is related to the deformation gradient. But then again the question would be, how does W look like? What's the mathematical form of W? Right. So there are so many models. For example, Sven-Venant model, New-Hookean model, Muni-Rivlin model for W. So here also we have to think about what should be the formula for psi, mathematical formula. So if we don't have clue about what should be the form of the energy function, the best is to write it as a quadratic energy, quadratic expression for the energy. I'm not the best, but it's the most intuitive thing to do right away. So you could, for example, write this as half of A times V1 square, maybe half of A1 times V1 square plus half of A2 times V2 square plus half of, let's say, D. Okay. Why am I using these constants A, D? Is because that's how it is used in literature. So half of D times V3 minus 1 square, because you see V3 is the axial stretch. So strain is V3 minus 1. So energy would be proportional to square of the strain, right? Plus half of well, let's say C times C1 times K1 square plus half of C2 times K2 square plus half of B times K3 square. Okay, that's the simplest thing that we could think of. There are many more quadratic terms missing here, right? Can you think of which ones are missing? The coupling terms, right? Where is the term corresponding to V1 times V2, V2 times V3 minus 1, the coupling terms. So, of course, that also arises, but this is the simplest thing. And it turns out this works for isotropic beams. You can also derive it mathematically from 3D elasticity, which we will do later on. But right now, we just wrote down a quadratic form of energy, and it turns out this actually works for isotropic beam. So this works for isotropic beams. Works for isotropic, I should say, circular beams. Okay. If it is circular, what happens is A1 and A2 are the same. So I'll just have it as A at both the places, and C1 and C2 would also be the same. And can you guess what will be A equal to? For example, just suppose this is your psi, what would be N1? N1 is del psi over del V1. Take its derivative with respect to V1, what do you get? A times V1. So shear force is equal to a constant times V1. Now think of your ordinary beam theory, Euler-Bernoulli beam theory or Timoshenko beam theory. What do you write your shear force equal to something times V1? What do you write over there? Do you remember? GA, right? With a correction factor also, isn't it? So KGA V1. Well, of course, now these two A's are confusing now. Yes. Anyway, so we have already used it. So, all right. So we can use it as a script, isn't it? A script, scripted symbol. T. I don't know how to write that. C. It looks like G, but I want to write it as C. Okay. All right. So that was your scripted A. So what you find out is that your A is equal to K times GA, and that's called shearing stiffness. Shearing stiffness. Similarly, if you want to get N3 axial force, that's del psi over del V3. And what's that going to be equal to? That's D minus V3 minus 1. And what do you use for ordinary beams? If you have a bar and you are stretching it, what's the axial force equal to? That's EA times V3 minus 1, right? So what that tells us is that your D is equal to EA. So D is actually stretching stiffness. Similarly, when you find out your bending moment M1, which is del psi over del K1, and that will turn out to be your C, scripted C times K1. And we know that this is also same as EI times K1. So C is equal to EI. And can you guess what will B be equal to? Scripted B. So your B is equal to GJ, right? So you see, you got all the constants also. So your energy function is now completely defined, well defined. Of course, we only took the quadratic form here. We could also have thought about using the cubic terms and the fourth order terms. But those terms get activated only when the strains are large. If the strains are moderate, if the strains are small, so if V1, V2, V3 minus 1, K1, K2, K3, if they are small enough, then just the quadratic form works, right? Linear material law. When does linear material law work? In 3D elasticity, linear material law works if the strains are small enough. Same here also for your elastic beams, elastic rods. This quadratic form of energy, which is linear material law, because forces are linearly related to strains, you can see here when you take the first derivative, forces and moments become proportional to strains. That's why it's a linear material law. So linear material law works if the strains are small enough, but if it turns out that strains are really large, then you have to include higher order term, or you have to think of nonlinear form from a more general perspective. So that's something we'll talk about later on, of course. But for now, just to get some feeling, we can think of this energy form, right? Okay. Now, if you think of, can we now solve our rod problem? Can we solve any rod problem once we have forces and moments connected with the kinematic quantities? Can we solve the equations of rod? You remember what was our unknowns? The unknowns were little r and capital R. Little r was the center line of the rod, and capital R was the rotation of the cross section. So these are the two quantities which we wanted to know, and the equations that we had was n prime plus n hat equal to 0, and m prime plus r prime cross n plus m hat equal to 0. So now that we have the constitutive law, we can plug it in here. So this becomes, or maybe I can write down below here. So this is big R times del psi over del V whole prime plus n hat equal to 0, and then this quantity becomes big R del psi over del k whole prime plus little r prime cross big R del psi over del V plus m hat equal to 0. Okay, so we are going to get some really nice thing. We'll completely derive the equations which all of you can actually code in MATLAB. You can use the MATLAB's boundary value solver. You can code it and solve any arbitrary rod problem. I think most of you are from computational background also, so you should really do that. All right, so let's take the derivative here and see what we get. So this becomes big R prime del psi over del V plus big R times del psi over del V prime plus n hat equal to 0. All right, so let's multiply the whole thing by big R transpose. So this becomes big R transpose big R prime into del psi over del V plus del psi over del V prime plus big R transpose n hat equal to 0. Okay. And what is big R transpose big R prime? That's your K, skew symmetric K. And since it's skew symmetric, it would be same as little k cross del psi over del V. right? Big K times del psi over del V is same as little k cross del psi over del V plus this thing. Now, what is that equal to? We want to take another prime here. So, now you can use chain rule. So, this becomes del 2 psi over del V 2 into V prime plus del 2 psi over del V del k, times k prime plus big R transpose n hat. So, you know what is this doing? You had your distributed load and it's being rotated back with big R. So, if you write your distributed load in the local frame of directors, so this is going to give you the components of the distributed load in the local frame of directors, isn't it? So, whenever you have a vector, you do big R transpose n hat, you get the components in the local frame of directors. Anyway, so we will just write it as n tilde now. So, n hat becomes n tilde, all right. So, that is equal to 0, and similarly we can also think of the second equation over here. So, that is the first equation. Then we think of the second equation over here. So, we have to go through the same process. Big R del psi over del k whole prime, you write it as big R prime del psi over del k plus big R times del psi over del k whole prime plus these terms. Once you have done that, then you pre-multiply by big R transpose everywhere. And what you would get would be k cross del psi over del k plus you will have del psi over del k whole prime, which will somehow become something like this. So, that would be del 2 psi over del k del v into v prime plus del 2 psi over del k into k prime. Then you have this term. Can you think of what's that going to become? So, this term has to be pre-multiplied with big R transpose. Maybe I will just write it over here. Big R transpose little r prime cross big R times del psi over del V plus big R transpose m hat. Now, because your big R is in SO3, it is a proper rotation, it simply distributes. So, you will have big R transpose into little r prime cross big R transpose big R del psi over del V. So, this is going to come here as well as here. Now, what is big R transpose little r prime? That is the strain V, right. So, this becomes k cross del psi over del k plus del 2 psi over del k del v times v prime plus del 2 psi over del k times k prime plus v cross del psi over del v plus m tilde. Just as we made it n tilde, we are making it m tilde. All right, so that's your moment equation. Yes.
Shouldn't the first K be a matrix second order answer?
This one?
Yeah, this one.
Yeah, so this was second order k is skew symmetric multiplied with del psi over del k, but then this is same as little k cross because it's skew symmetric, right? Okay. Now, can we use to solve our rod equations? So, let us look at the equations. You can see everything here is in terms of v and k. This is k. If you know your energy function psi, this is simply del psi over del v. You can very well use that energy function also, or you can use any arbitrary energy function also. You just take the derivative, you still get something in terms of v and k. So, this is also in terms of v and k, that is also in terms of v and k, then you have v prime. So, you see everything here is in terms of v, k and its derivatives, and this n tilde is the prescribed load from external, is externally prescribed load, distributed load. Now, this n tilde, if you are prescribing load, let us say in the vertical direction, then it has to be some big R transpose that load. So, here that big R is going to sneak in. This n tilde is actually big R transpose n hat, right. So, everything here is in terms of v and k, but over here you have a big R also showing up. Similarly, you come down here, everything is in terms of v and k, but in the final m tilde you have big R also showing up. So, can we, and you see, so it is first order in v and k, but then you also have a big R. Can we use this to solve our equations, get our small r and big R? We can also think of it in a different perspective. So, we see things in terms of v and k and its derivatives. Why don't I plug in the formula for v and k in terms of little r and big R? For example, v is big R transpose little r prime. We start plugging in everywhere, wherever v is there, you plug in big R transpose little r prime. Then you see v prime. So, you have to take the derivative of big R transpose little r prime. So, it becomes second order in little r, right. And similarly, you will have big R as a second derivative. Wherever you have k prime, when you substitute k equal to big R transpose big R prime and then take the derivative, it becomes second order in big R. So, if you look at it from that perspective, then the two equations, you have 6 equations only in terms of little r and big R, but they are second order, isn't it? So basically you can, so there are two ways to look at. One is, why don't I substitute V equal to big R transpose little r prime and K equal to axial of big R transpose big R prime. So you do that, and then the two box equations, they are going to become second order in little r and big R. Second order in every one of them, little r as well as big R. So how many boundary conditions do you think you will need to solve it? So it's second order in both little r and big R. So in this framework, you have 6 equations and 6 unknowns, so you can solve it, right? Because everything is now in terms of little r and big R, and it's second order. So how many boundary conditions do you require? So little r has got 3 components. It's second order in each of the 3 components. Big R, if you use axis angle representation, you can write it in terms of a theta vector having just 3. So big R also has got just 3 independent unknowns, right? And it's second order in those 3 unknowns. So it's, so you've got 6 unknowns, and it's second order in each of the 6 unknowns. So how many boundary conditions would you require? Right? It's second order. If it were first order, you would hit just 6. If it is second order in each of them, so 12. So you need 12 boundary conditions. 12 boundary conditions. Think of a very simple cantilever problem that we solved using Euler-Bernoulli or Timoshenko beam theory. Can you think of what are those 12 boundary conditions? So one end is clamped, and the other end you have a load acting, which is P times E1. So it's always in the E1 direction. So you see, you have to get 12 boundary conditions. Think of Euler-Bernoulli, it requires very little, just 3, I guess. And if you have more unknowns to write down the profile for bending moments, then you need a little more. But here you need 12 boundary conditions. It's a 3D problem. The beam can also come out of the plane if you apply such a load. So can you identify those 12 boundary conditions here? So look at the clamped end, for example. What are the boundary conditions over there? Yeah?
I would say everything is 0.
Everything is 0.
Yeah.
So let's write in terms of the kinematic variables, little r. So little r at 0 is equal to 0. So this has got 3 boundary conditions, you see. It's a vector equation, little r1, little r2, little r3. All 3 of them are 0. It's clamped. What can you say about big R? The rotation at 0. It is clamped. 0. Big R cannot be 0 ever. It's SO3, so it's identity. And if you were to write it in terms of theta, if you use theta to represent big R, then that's exponential of theta, skew symmetric theta. So, that would imply the little theta axial vector. So, that little theta is equal to 0. So, exponential of 0 matrix is identity. So, that little theta which has 3 components, that is equal to 0. Okay, so, again here you got 3 boundary conditions, 3 plus 3 is 6. So, you got half of them. So, look at the other side. What can you say about that? Can you say something about little r? We can't say anything about little r. You see, force is prescribed here. So, n, that little n is prescribed over here. N is equal to p times E1. So, n is equal to p times E1. But then we have to write this n in terms of the kinematic variable, which is simply big R times del psi over del V. So, this is same as big R times del psi over del V at 0, sorry, at 1 for example, or L, that is equal to p times E1. So, this is not such an easy boundary condition. When you expand it in terms of little r and big R, you get a complicated expression. Okay, so, that is p times E1. So, you got 3 more, right? This is a vector equation, 3 equations here, 3 plus 3 plus 3, 9. What is the other one? Yes? Moment, right? What is the moment at this end? 0, right? So, that says big R times del psi over del k at L is equal to 0. And you can very well get rid of big R also here. Just multiply by big R transpose, this goes away, then del psi over del k at L is also equal to 0. That is because since the moment is 0 here, the moment is also 0 in the local frame of directors. Therefore, del psi by del k is also equal to 0. So, those are your 12 boundary conditions. Okay, we identified the 12 boundary conditions, but you see it's still not so easy to solve. Why? Because big R, when you think of writing it in terms of this theta, exponential of theta, so it's a very messy equation. So, it has got severe nonlinearity. You remember that Rodriguez formula? It has got sin theta, cos theta, axial vector. So, it is not so easy. Of course, there are formulations to solve it in terms of little r and theta, but it is not so easy. We want to solve it in terms of quaternions, for example, something that you guys can go back to your computer and code in MATLAB very easily, instantly. You can of course code this also, it is going to take some time, all right. So, when right now when we are seeing it, it's a we just got 6 equations and they are second order. Now I like to reframe it as a system of first order equations, something that MATLAB requires. Your BBP solver, it requires first order equations, and you will see it doesn't look so bad.
Is there any benefit in taking another prime on the moment equation and eliminating n from that? You know, like having n
Yeah.
double prime.
Yes, of course
Plus
you can
whatever.
do that.
Is there any good in doing that?
But you would still
You get a higher order.
yeah, but then you still require the first equation, right? Because you need that many equations. You have 6 unknowns, so you would still require 6 equations. It's just that the second equation has got less term now, but you still require first equation.
Yeah, I think,
Okay, so that was one perspective, thinking of it as a system of second order equations. The other perspective is we want to think of it as a system of first order equations. System of first order equations, so that we can use commercial solvers. And when we see these boxes, these are already, as you see, they are first order in V and K, right? But then you also have your big R sneaking in there. See, in n tilde and m tilde, you have big R also. Plus, the boundary conditions also have your big R and little r. So, you have not been able to eliminate big R and little r completely. You see, the boundary condition here is in terms of little r. It's not in terms of V and K. If it were in terms of V and K only, then it becomes a closed system, and then you are done with these two equations. But it's not a closed system now, because you have little r and big R also showing here. So now we want to think of little r, big R, V and K as independent unknowns. Okay? So then of course we need more equations. Little r has got 3, big R has got 3, V has got 3, K has got 3, so 12 unknowns. So we need 12 equations. And as of now, we only have 6 equations here. So what will be the remaining 6 equations? Can you guess? Which identities?
First order derivative is equal to first order derivative, right?
Yeah, exactly, yes. I mean, relating this with this. Relating little r with V. And you already have that, right? That little r prime is equal to big R times V. Isn't it? That's how V was defined. V was big R transpose little r prime, right? So little r prime is equal to big R times V. What about the other equation? So that was big R transpose big R prime equal to K, right? So that means big R prime is equal to big R times K. But I really don't want to work with this big R. I want to work with quaternions. Sorry. Okay. So this is fine, but this is something I want to get rid of, because I mean I have seen it, it becomes very messy. You can also see it when you work it out, but quaternions it becomes easier. So if I represent my rotations in terms of quaternions, then we have this matrix Q prime. So Q, remember that quaternions Q0, Q1, Q2, Q3. Then Q prime, it turns out to be some matrix E into your K, that little k which is here, and that E matrix that's equal to half of so that's a 4 by 3 matrix. So Q prime is equal to this matrix E times K. So you can derive it, of course. I haven't derived it, but take it as a known fact. You can also derive it. And this equation is such that it also satisfies that the norm of Q remains 1 always. You know, the Q has to be such that its norm is equal to 1. So which means Q dot Q has to be always equal to 1. So that means Q prime dot Q should be equal to 0. If you take this matrix and dot this with Q, so you find out Q dot Q prime, and if you have this Q E matrix, you will see that this will automatically become 0. For any k, this becomes 0. So we don't need that constraint as an extra equation, that Q dot Q equal to 1. That's not required here, because this equation automatically satisfies that constraint. Anyway, so let's look back at our system of equations. So I look at the first equation over there, which is little r prime is equal to big R times V. And this big R, you must remember how, I mean, you don't have to remember, but you can note from last lectures that we had written big R in terms of quaternions. I can write it down again. Should I write down again? You can refer back, right? So big R we had written in terms of quaternions. Okay? So that's for small r. Then you have Q prime, little q prime equal to big E times K. So you see, the way we want to write it down is that we should have the unknowns, the derivative of the unknowns on the left hand side, and on the right hand side we should not be having any derivative. That's how the first order equations should be written. So as you see here, on the right hand side there are no derivatives. Here also there are no derivatives. All the derivatives are on the left hand side. Think of using then the force balance equation. You have a derivative in V and K. right? So we want to have that on the left hand side. Okay, I'm going to write both of them together, and I'll show you how that becomes. See, I wrote down those two equations as a matrix equation here. You can see, look at the first equation, this times this equal to this number minus that number. Can you see it's the same thing over there? And similarly for the last equation also. So once you have done this, you have to just bring this matrix on the right hand side, and this is also called the elasticity tensor for rods, because you see its second derivative in the strain measures. In 3D elasticity, you would have del 2 W over del F2, that's the elasticity tensor. So here this is also the elasticity tensor matrix. 6 by 6, it's a 6 by 6 matrix, elasticity tensor matrix. And it has got very nice properties, just as in 3D elasticity. In 3D elasticity, they have to be rank 1 convex. You will learn in your nonlinear continuum mechanics course. But here, when you use that rank 1 convexity, this turns out to be positive definite. So this matrix is always positive definite. So that's a very nice thing. It's positive definite, so equations are very well posed. You can take it also on the right hand side, and this becomes, so you see you have these two equations, and then you have Vk prime equal to this matrix, that's the elasticity tensor. If you allow me to use big C for that, big C inverse, because it comes on the right hand side, times this whole thing, so with a minus sign, of course, k cross del psi over del v, and then k cross del psi over del k plus v cross del psi over del v plus big R transpose m tilde m hat, and here you have big R transpose n hat. Okay, so this comes with a minus sign here. So can you see how many equations you have? 3 equations here, 4 equations here, 3, 4, 7, 3, 3. 13 equations for the 13 unknowns, little r, little q, v and k. System of first order coupled nonlinear ordinary differential equations. Why is it nonlinear? Can you see why this is nonlinear? It is first order because you see all the derivatives are only first orders. There are no derivatives on the right hand side. Why is this nonlinear? Just look at this term, for example. This big R is in terms of quaternions, which is an unknown, and V is also an unknown. So it's quadratic, right? It has quadratic nonlinearity. So it has actually cubic nonlinearity because big R itself is quadratic in quaternions. Big R matrix is quadratic in quaternions. It has Q0 square, Q1 square, and then you further multiply with V, so it becomes cubic nonlinear. This is quadratic nonlinear because your big E is linear in Q times K, it's quadratic nonlinear. Then you come over here, if you use quadratic strain energy function, if your psi is quadratic, the one that we were using, the psi was quadratic in strains, then what can you say about this matrix? This would become constant, right? You take 2 times derivatives, you only get constants. So it's a constant here if you use quadratic. If you don't use quadratic, then it won't be a constant. So you see, this formulation is not restricted to quadratic energy function. You can use any energy function you feel like, but then this won't be a constant. But if it is quadratic, this is a constant. You look within, this is quadratic. If psi were quadratic, then the first derivative is linear, this is also linear, product of linear becomes quadratic. Okay, so you can identify each of the terms, what's the nonlinearity. So you have 13 equations, right? So system of 13 coupled nonlinear ODE. So we are done with writing the equations. So you see, this is very easy. You can go and write in your MATLAB. You should do that. But this is not done yet. You just got the equations. You now need boundary conditions. Yeah, please erase. So we can again go back to our cantilever problem and identify the boundary conditions. How many boundary conditions would you need now? It's a system of 13 first order ODE. How many? 13, right? So instead of 12, you now require 13 boundary conditions. One extra. So you would have to identify what's that extra boundary condition. Okay? So, let us again think of solving the cantilever problem. And the load acting is PE1, and we want to think of the boundary conditions. And the boundary conditions have to be in terms of the unknowns, little r, little q, little v, little k, right. So, we come to the clamped boundary condition, and we have, as we had earlier, little r of 0 is equal to 0. So, that is in terms of the unknowns, very well. Then we think of the rotation boundary condition. Now, rotation is identity there. What will that be in terms of quaternions? So, you have to then remember how to write quaternions in terms of axis angle representations. Okay. So, your q0, for example, was cos of theta by 2, where theta is the magnitude of rotation, and q1, q2, q3, if you write in a vector form, it is sine of theta by 2 times the theta hat vector, or the axis, the unit axis vector. Okay. You could also write it as A, the axis vector, unit vector. So, that is how the quaternions were related to axis of rotation and the angle of rotation. Now, over here rotation is identity, there is no rotation, angle of rotation is 0, right. So, just use here theta equal to 0, q naught becomes 1, this is also 0. So, this whole thing is 0. So, what this tells you is that q naught at 0 is equal to 1, and q1, q2, q3 they are all 0. So, you see you got 4 boundary conditions from rotation, 1, 2, 3, 4. So, that is the extra one. Then you think of the right hand side for the load, and it is simply big R del psi over del V at L is equal to PE1. Big R you can write in terms of quaternions at L times del psi over del V is in terms of V and K at L. So, everything very well written here. Similarly, for the moment, which is del psi over del K at L equal to 0. So, you have got those 13 boundary conditions, right. So, can you solve it in MATLAB? You can use the BVP solver. You have the boundary condition, you have the equations. What will the C matrix look like for the energy function that we had? So, if we use that energy function, C is simply a diagonal matrix which will have KGA, KGA, EA, EI, EI, GJ. So, C becomes a diagonal matrix, and the non-off diagonals are all 0. Okay. So, this is something you should be able to solve. Cantilever problems are of course not so exciting, but then you can compare the results that you get with the Euler-Bernoulli solutions and Timoshenko beam solutions. and check what's the difference that you get. You can also solve an exciting problem, a more exciting problem, which is called the follower load problem. So this is called follower load. So it's very much like the cantilever, but just that the load follows the deformation. So as the beam deforms, the load, the direction of the load also changes. So the load here is not PE1, it is PD1. So as the beam deforms, for example, if the beam deforms like this, load is acting this way. Okay. Can we identify our boundary conditions? You see, the clamped boundary condition is the same as earlier. Then on the right hand side, moment is 0, so you have the same boundary condition. But for the force, you have to say big R del psi over del V at L is equal to P into RE1, or just R times PE1. And this is a much easier boundary condition actually, because this R cancels and it's just that del psi by del V1 is equal to P, then del psi by del V2 is equal to 0, and del psi over del V3 is equal to 0. This is much easier boundary condition compared to the cantilever boundary condition. So it turns out in this formulation, solving the follower load is easier than solving the cantilever. The boundary conditions are certainly easier. And when you solve it, you change your load. As I told you, you get exciting solutions. So you will see something like this. You should really try to solve it. At 0 load, it is straight. As you increase the load, it will become something like this. So that's a higher load. This is even higher. And then it actually comes back. If you further load it, something like that. So it looks very exciting, right? Okay, so can you solve it in MATLAB? Okay. All right. Do you want to show me next time when you come? You remember we had one more example in the beginning which could not be solved using Euler-Bernoulli or Timoshenko beam theory. Let us see how we can solve that problem using rod equations. So, the problem was that's a problem. We had a load acting here. So it's a collar, frictionless collar, and you are applying load P. And you could make it even more exciting. You can also apply a twisting moment here. Then it starts to rotate. It undergoes 3D rotations, 3D deformation. So you can apply, let's say, ME1. So big ME1, of course. No, it's little m. Okay, and that's PE1. So equations are the same, right? But then we have to identify the boundary condition. So again, on the left hand side, we have the same boundary condition, that little r of 0 is equal to 0, and q at 0 is equal to 1, 0, 0, 0. What about the forces over here? So this is really complicated boundary condition. Can you now think of what should be the boundary condition? See, it's a frictionless collar and you are applying a load P here. So, what can you say about the contact force over there? Okay, let's forget about the contact force. Think of, I'm sorry, think of the kinematic boundary condition, for example, the little r over here. What about little r in this direction? It's prescribed, it's not 0, it's L, right? In this direction. What about little r in this direction? 0, right? It can't go in this direction, but in this direction, that we don't know. So we can say that little r of 2 at L is equal to 0, then little r of 3 at L is equal to L, but little r of 1 we cannot say. So, if we can't talk about the position, then we can talk about the forces. So, the n, so we would know that n1, the force in one direction, n1 at L is equal to P, right? But we want to write this in terms of the unknowns, little r, q, v and k. So, this is just n1. We want to write down n1 in terms of those unknowns. So, how to write that? So, it is simply, so n, your n vector is big R del psi over del v. and I want to get n1, so take the dot with E1, right. So, big R del psi over del V dot with E1, that is equal to P. So, this is that equation. You can even simplify this. What kind of rotation is happening there? Can you see? The rotations are such that it only rotates about E1 axis. So, think of the director D1. Where is the director D1? If the rotation is about E1 axis, so D1 will be equal to, what's D1 equal to? It's R times E1. But since the rotation here is about E1 axis, so D1 is same as E1, right. So, this P is also your big N1. So, little n1 is same as big N1. Now, in terms of big N1, then the boundary condition will be very easy. Why? Because big N1 is same as del psi over del V1. So, you either write this or you write del psi over del V1 is equal to P, only for this problem, of course. So, that is a easier boundary condition. So, that is for the forces. Then we think of the moments. So, as we just found out that the rotation is about E1 axis. So, your A vector is known, right. The vector A is your E1. So, the quaternions, how the quaternions are to be written? Q naught is equal to cos of theta by 2, where theta is the angle of rotation, that is unknown here. So, we can't say anything about Q naught, but Q1, Q2, Q3 this is such that this is equal to sine of theta by 2 into the axis of rotation, and the axis of rotation is 1 0 0. So, although theta is not known, but this times 0 is always 0. So, what you can prescribe here is Q2 equal to 0 and Q3 equal to 0. So, you already got those two boundary conditions. So, one more is remaining. What is that one? You see, the moment is prescribed there, bending moment is prescribed. So, how do you write that? So, that is the moment along E1 direction that is prescribed, and since E1 is same as D1, so that is also the bending moment along D1. But what is the bending moment along D1? Del psi by del K1, right. So, that means del psi over del K1 at L is equal to little m, right. So, your boundary conditions I will write again is that little r at 0 is equal to 0, q at 0 is equal to 1 0 0 0, then r2 at L is equal to 0, r3 at L is equal to L, then del psi by del V1 at L is equal to P, then Q2 at L is equal to 0, Q3 at L is equal to 0, and the final one is del psi by del K1, del psi over del K1 at L is equal to m. So, here it is, the 13 boundary conditions. Okay. All right. So I think I'm already running out of time. In the next class, you should also solve. You should solve this in MATLAB. But Smriti and Prakhar, they will also present some examples, some nice examples that will be solved in MATLAB, and it will be presented to you. You can see what kind of crazy shapes you can get when you solve using rod equations. And once that is done, then we will talk about this energy function from a more general perspective. See, today what we did was more like hand waving. So we just wrote down the quadratic energy expression. But we want to talk about it in a more rigorous sense, how to get this from 3D elasticity. Not just the quadratic, but any nonlinear energy function. For any arbitrary V and K, what should be the psi? So we'll talk about this in the next class. Okay? So see you in the next class.
Which is Tuesday.
Tuesday.